At its simplest, working is the energy added to or removed from a system by a force, F, over some displacement, delta x. Much of the time, when we talk about work, we're going to be talking about work in the context of a single object system. If you think about a single object system, so one example of that would just be a box, and then anything else interacting would be outside the system. Okay, so we'll put all this stuff here. These are things that the box could be interacting with. But if our box is the system and everything else is outside the system, the only kind of energy a single object system can have in itself is kinetic energy. All other kinds of energy are interactions with other things, and so they properly don't belong to that system. So a really simple example of a single object system would be, object, let's just call it a box. So your box starts out with no kinetic energy. You kick the box, and then it has some kinetic energy. So your energy accounting equation, because energy is not conserved, would be the starting kinetic energy plus the work done on the system, or the working done on the system, equals the final kinetic energy. Now, so I guess one thing is you can sort of identify if working is happening on your system by whether the initial energy and the final energy are the same or not. If they're different, that means you have some sort of energy entering or leaving the system. Yeah, let me say that one more time. So if you have your system, if the initial energy of the system is not equal to the final energy of the system, then you have energy entering or leaving, and you can figure out how much working has been done by taking the final energy and subtracting the initial energy. Here's a sample problem. A 160-gram hockey puck is moving 5 meters per second just after being hit. After traveling 8 meters along the ice, the puck is moving a bit slower, 4.5 meters per second. How much work was done on the puck by the ice? So this is a single object system. It's just the hockey puck. And if we made an LOL diagram to help us visualize what's going on, we have the puck. All it can have is kinetic energy. That's the only account. It's moving 5 meters per second just after being hit. So I'm going to say that's like 6 boxes. And after traveling 8 meters along the ice, it's a little bit slower. So let's take some boxes away. So if we were writing this down before, we would say that 1 box of work has left the system. But let's be a little more quantitative now that we can. Okay, so in the beginning, how much kinetic energy do we have? We can calculate that as 1/2 times the mass of the hockey puck times its speed at the beginning squared. So 1/2, 0.160 kilograms times 5 meters per second squared. And when I put that in my calculator, I get 2 joules. See, the units will be kilograms meters squared per second squared. That is a joule in named units. So we start out with a kinetic energy of 2. At the end, if we have a slightly slower speed, that works out to be 1.62 joules. Our energy in the beginning plus the work done on the system is equal to the energy the system has at the end, which means if we want to solve for the work that was done on the system, we get that by itself. Work equals final energy minus initial energy. And now we plug in our numbers, 1.62 joules minus 2 joules equals negative 0.38 joules. So the work done on the system here is negative. That kind of makes sense. We're removing energy because the object gets slower.